Welcome back to ECE 220. We're coming in on the home stretch. We're in the last chapter, chapter 9, and also Appendix B. But I thought I would try to give you a little warning in terms of heads up on some of the dates that you don't need to attend and one that you definitely need to attend. We will not have class the Wednesday before the Thanksgiving break, which I believe is the 27th. Our exam will be the following week. Exam number 4 is on the 5th of December, and then we will not have class on that following Friday after exam number 4. And we will not have class the last day of class. That's not on here, but that's where we're at. Those are the next 3 classes that we will not meet. And Group A, you are beginning your final lab this week. Lab number 5 is this week, and it deals with first order circuits, RC circuits, and also sinusoidal steady state, and now you're going to be doing that in the lab. Your homework number 12 is due tomorrow. That's dealing with RLC circuits. And Group B, you need to be finishing up lab number 4. Your report is due Wednesday, and your pre-lab for lab number 5 is due Saturday. What we're doing today, last time we talked about sinusoids, how we can figure out where they are, leading and lagging. We also represented those with these complex quantities called phasors, and today we're going to focus more on that topic, which is phasors and complex numbers, converting back and forth between rectangular and polar, looking at what complex numbers, what we have to do with them versus normal numbers in terms of the different operations, addition, summation, or subtraction, multiplication, division, etc. Then we'll talk about Euler, rotating phasors. We'll try to give some pictures of that with time response waveforms and these rotating phasors. Then we'll get into some exercises, although we're going to be doing exercises from the beginning. So here's our Phasor transform. If you are now presented with this time domain waveform, here we have 2, but let's start with the first one. 5 cosine of 200t plus pi over 3. And that pi over 3, if you're not used to seeing that in radians, I've picked it conveniently. 180 divided by 3, that's 60 degrees. This is now cosine of 200t plus 60 degrees. And you'll see the argument of these sines and cosines expressed in either, well, the phase expressed in either radians or degrees interchangeably, and you just need to be comfortable going back and forth. What or how would we write the Phasor transform of that time domain expression, the first one? What do we pull out and what do we keep on the side if we are now trying to find the Phasor representation of that time domain waveform? We have 3 quantities floating around: a magnitude, a frequency, and a phase. We actually put the frequency on the side. We just need to keep track of that. If we're talking about sinusoidal steady state, everything is now oscillating at that frequency, and we can sort of keep that on the side. And what we're interested in are the magnitudes and their phase shift or time relationship. That means then that we are, I don't want to do it in red, not this early on a Monday. It is Monday, isn't it? Who knows? I'm not getting any response from the audience, so I'm just going to go ahead. That's 5 at an angle of pi over 3. Or you could have written that as 5 at 60 degrees, converting the pi into 180. So those two answers would be equivalent. What about the second one? Is that okay? What you need to keep track of are the alarm bells that go on in your head when you see a sign, because we are actually sticking with the cosine when we're doing our Phasor transform. So that magnitude is okay, but now how would we convert this into a cosine? What's the equivalent cosine expression? How do we need to modify the argument to turn that into a cosine? How are sine and cosine related? The sine is behind the cosine, or lags the cosine by 90 degrees. We can now convert that sine into a cosine, do the Phasor transform on the cosine, and now we can obtain the correct answer. Or we could have written that as minus pi over 3. Either of those would have been okay. And what we want to keep track of then is that this is trying to help us. We're trying to simplify, not having to keep track of all these sines and cosines. But now, when we are playing with phasors, the phasor is a blank, and here I'll give you a hint, number. Is it an imaginary number? Is it a funny number? Is it a real number? I'm avoiding the answer. None of the above. What is it? It's complex. I could have started today by saying, today we're going to have a complex discussion. And it would have been true, but it wouldn't necessarily have been difficult in the notion of complex, but it's just now we are playing with complex numbers, and we need to get comfortable with that. So now we're converting these real quantities, these v of t's, these I of t's that are cosines and sines. We're keeping the frequency on the side, the omegas, whatever that is, and we convert those time domains into complex numbers, into a phasor representation. So let's now get the wheels turning in terms of being able to go back and forth, and sometimes it's convenient to have it in rectangular form. Sometimes it's convenient to have it in polar form. Sometimes it's convenient to have it in both. And to have it in both, you can sort of draw a picture. That helps you, I think, keep track of what's going on. Here is the real component, that's x. Here's the imaginary component, and when we go imaginary, we basically say, oh, you're going in the vertical direction. You indicate that by scaling it by the square root of -1, or j. You now have this x plus jy as a point, or you can view it as a vector, and now this z is located on a plane with a real part equal to x and an imaginary part equal to y. That's the rectangular form. We can also look at it as, or in an exponential form, z e to the j theta. Now we're dealing with the distance, or the length of that vector r, and its angle that it makes in a counterclockwise direction with respect to the positive real axis. Again, we're going to a particular point in space, but now we are getting there by saying how far are we going away from the origin, r, and in what direction, theta. Or we might write that, since it's just really keeping track of two numbers, we have a shorthand. I guess we don't want to acknowledge Euler as much as we should. We convert the r e to the j theta and just say, oh, write it as r angle theta. Those are the same thing. It's just a different way of expressing the same information, and a lot of times we just call them both the polar form. Maybe we don't want to say exponential, but both forms are often called the polar form. Those are going to be interchangeable. Polar form, exponential form, and then contrast that with the rectangular form. Here's an example. Z is equal to 3 plus J4, and I've picked those numbers for ease of computing the distance that they are from the origin. We now go 3 horizontally, we go up 4 vertically, and we end up being at that location, and we could say, oh, that's r at an angle of theta. And what is r? That's the hypotenuse of a right triangle. That's now this square root of the real part squared plus the imaginary part squared. And I said I picked those numbers conveniently so that I now have the square root of 25, which is 5, for my distance. The angle is not so convenient, maybe, but that's now, going back to our trig, that's now the opposite side, 4, over the adjacent side, 3, and this angle comes around a lot when we're dealing with complex quantities. That's now 53 degrees, and you can sort of eyeball that if you've sketched. And that's why I like to sketch, is you can sort of use that as your guide or your answer in the back of the book. You can say, I'm not getting what I just sketched as far as the number out of my calculator. Hopefully this will now help you, and what you need to make sure is that you pay attention to the quadrant. When you start moving in an opposite direction, you need to make sure that you know, is that in the real direction that we're going opposite, or in the vertical direction, imaginary direction, because it changes the value of theta. You can't just say, oh, it's a negative. You have to tell us where are you going negative, vertically or horizontally. That's going to influence the angle. Here's the conversion. Now I'm just checking your memory. We can keep track of about 7 things at once in our head. You can probably keep track of more. I can maybe keep track of less. But how do we relate r and theta? If we now have a complex number in rectangular form, now we can say, oh, we're over here at x, j, y. Now we just have to deal with right triangles. We have the hypotenuse, and we have that angle, where this is now the square root of the real part squared plus the imaginary part squared, and the angle is the inverse tangent of y over x. Oh, I don't know if I told you or not to watch the quadrant. Can I make that any more known? Pay attention to which direction you're going when you're finding the angle theta. Are you going y or x if it's actually negative? Conversely, if you now have a polar form, which now you're starting with this r and theta, that's maybe what you were given, and you can, maybe I'll include that on your list of available things to bring. Maybe I'll allow you a ruler and a protractor on your, you won't need it for exam 4, maybe on the final. So now you have, well, maybe you can purchase these on Black Friday. If you don't already have a ruler and a protractor, now maybe they'll be at a whopping deal on Black Friday. How do I find x? Now that I've used my protractor and my ruler to get me to that point, now you can just project onto the real axis to obtain x. We're now saying, oh, that's r cosine of theta, and we can project over onto the vertical axis. Now we're going vertical, so we have to precede that with j, telling us that that value is now in the vertical direction, but the value y is simply r sine of theta. Now we have these two representations. Z is equal to x plus jy, rectangular, plus r at an angle of theta, that's in the polar form, or in the exponential form. And now I want to acknowledge where this e to the j theta, who's associated with that, what name, so that now we can say, oh, just apply Euler. I was going to ask you, but now I've already given it away. Euler. Euler now allows us to say, oh, e to the j theta, that's, and what's the magnitude of e to the j theta? That's a point in this complex plane. It's an angle theta relative to the real axis. But now if you just look at what Euler is giving you, you say, oh, it's the square root of the real part squared plus the imaginary part squared. Cosine squared plus sine squared is 1. Now when you see e to the j theta and somebody says, oh, what's the magnitude of e to the j theta? No matter what theta is, if they don't scale that, if they don't put a scaling factor in front of the e to the j theta simply has a magnitude of 1. And I'm assuming everyone has heard the joke. Now I've forgotten the joke, but, and don't get me in trouble if I say this, but on one of those reality shows one time, they were, it usually has some male and female things going on, but this one was about this was Beauty and the Geek, I think, something to that effect. Anyway, they obtained their geek from MIT, and this is just the notion. He walks up one of the first days of class or on campus, and he walks up to a female on a bench, and he says, oh, you must be sine squared. She looks at him kind of with a weird face, and she goes, what? He goes, you must be sine squared, because I'm cosine squared, and together we're 1. So now sine squared plus cosine squared is 1. I don't know. Anyway, when you see e to the j theta or think of Euler, you'll be seeing this, maybe thinking about the joke. Oh, okay. Anyway, sine squared plus cosine squared is equal to 1. Addition and subtraction. When are they better or easier to perform? In what particular form of the complex number is it easier to add? In rectangular or exponential or polar? What would you expect? If we're now adding and subtracting and we have these two possibilities, x plus jy, if we're now adding z1 and z2, how do we want to represent those, or what's the easier way to add those? What form do we want our complex number in? Probably in its component form or its rectangular form. That makes it easier to perform addition and subtraction. You just have to add or subtract the component parts, the x components and the y components, the horizontal components and the vertical components. Conversely, multiplication and division, now it's easier if you have it in terms of magnitude and angle, or in the exponential form. Or the polar form. And here is a summary of various operations. Suppose we now have z1 expressed with subscripts of 1, x1 plus jy1, or r1 at an angle of theta 1. And you know how to relate those. If you're given r1 and theta 1, you can find x1 and y1. If you're given x1 and y1, you can find r1 and theta 1. I hope that you're now convinced that it's not that difficult to play with complex numbers. You just kind of have to keep track of things. So chapter 9 really is just a remake of chapters 3 and 4. It's just now we're playing with complex numbers instead of real numbers. Addition. We just add the components. Subtraction. We subtract the components. Multiplication. Now we just have to multiply their magnitudes and add their angles. And why is that? Why can we get away with just adding their angles? We have z1, which is r1, and now let me write it more explicitly in the exponential form. And now we can use the exponential, or the properties of the exponential, to combine those exponents, and those combine by adding. So the reason we're able to add and subtract angles in the multiplication and division is because really underneath that shorthand symbol or strategy for writing these exponential numbers in polar form is the fact that we can add exponents and subtract exponents depending on whether they are multiplying or dividing. That's where those are coming from. So this is designed to be up there. Division. Instead of, if they were in rectangular form, you could rationalize the denominator by multiplying by the conjugate if they were in rectangular form, but then you can't just multiply by a number. You now need to make that scaling factor 1, which is now the conjugate divided by the conjugate. That's just a little messy. This looks a lot easier to say, oh, just take the ratio of their magnitudes and subtract the angle of the denominator value from the numerator's angle. If we take the reciprocal, 1 over z1, again, playing with this exponential form makes it a little easier to understand why you can just negate the angle in that polar form. Now we simply take the reciprocal of the magnitude, and subtract the angle. And now we've inverted that complex number, which is easier if it's in exponential form. Likewise, if we want to take the square root of a complex number, if it's in polar form, that's a little easier to think about. Now we just take the square root of the length of that vector and we halve or divide the angle by 2. And that's now the square root. So if you need to take the square root of some complex number, it's not that intimidating of a idea. And what could somebody do? They could give you the square root of some complex number in rectangular form, and you might go, but convert it to polar form, and then it's fairly easy to extract the square root. The conjugate is when you simply change the sign of the imaginary component. x1 minus jy1. And in fact, if you're looking at that in the complex plane, if this was x1 and this is jy1 and we were up here, now the fact that we have negated y1, now we're just down here. And if I had drawn that properly, hopefully you see that this angle is just the negative of this original angle theta 1. We've just mirror imaged that or rotated it around the real axis. J squared, okay, that's minus 1. You're used to thinking of it that way, but another way of thinking about it is when you now start multiplying j's, you're really rotating by 90 degrees. You can see that in the exponential form. You have e to the j 90 degrees times e to the j 90 degrees. Well, we can now add those exponents. We now have e to the j pi, or e to the j 180. We've now moved from 90 to 180. We're just stepping with 90-degree steps. So that now if you were at 90 degrees, that just means you're at j1. Now you want j squared. Oh, I square the magnitude. The magnitude was 1. Remember our joke? So we just have a sine component. We now square that magnitude of 1. We get 1 back, but now our angle has changed. It has advanced 90 degrees. We're now at 180. Similarly, if somebody now wants to invert j, what does that do? Well, you can multiply it by 1, which is j over j. Now you have j squared in the denominator. That's minus 1. That can be absorbed into the scalar, so that now 1 over j is just minus j. Or j to the minus 1, again using our knowledge of exponents. That's e to the j 90. And now we negate the exponent when we raise it to a power of minus 1. And now we're below the real line at an angle of minus 90 degrees. Or rationalization or reasoning behind 1 over j being minus j. And we'll just do that routinely. If we now have a j sitting in the denominator without a real component, with a real component, then you have to incorporate the real part. Now the real part of z, if z is x plus jy, we now have that as x, and the imaginary component is y. acknowledging Euler, we have e to the j theta is cosine theta plus j sine theta. Now we can rewrite sines and cosines as parts of a complex phasor. Cosine theta is now just the real component of e to the j theta. If e to the j theta is cosine theta plus j sine theta, and you just want or just need cosine theta, just take the real component of that complex exponential. Likewise, the sine of theta is the imaginary component of e to the j theta. This is what we were all coming to class for, is to figure out how to simplify. And what we're doing this for is to avoid differential equations and convert all of this differentiation integration into multiplication by complex numbers, so that now we can do algebra with complex numbers. Now we can rewrite these time domain waveforms v sub m cosine omega t plus theta as this real part of v sub m cosine wake me up. I went inside a real operator. That means that I can rewrite that cosine as its complex exponential if I'm just taking the real component. Or now I'm going to say, oh, e to the j, and what was the argument? That was omega t plus theta, and that's now v of t. V of t is now the real component of this magnitude, v sub m, e to the j omega t plus theta, our complex exponential. Now let's rewrite that as a product of exponentials. E to the j omega t, e to the j theta. And we can reorder those product terms, the two on the right, let's interchange. We can now say, oh, that's the real part of v sub m e to the j theta e to the j omega t. And now we can rewrite that. That, in fact, is just a complex number. It's not time varying. The time varying part is in that complex exponential e to the j omega t. That's where t is floating around. Yes? Yes, so the question was, why are we doing all this complex number gymnastics? So that we can get in shape. But besides that, it's going to allow us to avoid worrying about the transient. Now we're just shaking this system. We know the transient doesn't last very long, so we're waiting until that is gone, and then we're in a steady state. And we want to now know, now that we're in this sinusoidal steady state, oh, there's easier ways to deal with this than playing with differentiation and integration. We can now do the algebra with complex quantities. So how we had been doing it, you cannot disregard. The question was, can we disregard? We can't disregard if we're dealing with the transient, which is really sort of what we were talking about mostly in chapters, keep me honest here, 6 and 7. No, 7 and 8. With the RL and the RLC. There we were worried about what's happening in this transient interval. We then needed to worry about these differential equations. Now what we're doing is we're going and saying, well, in those chapters, we were typically either starting with initial conditions or just exciting our system with constant waveforms. We wanted to move beyond that. We now know that the world is full of frequencies, sinusoids. Can we now come up with a strategy to analyze systems that are excited or involve sinusoidal signals? That's why we're doing all of this. So now we can collect this complex piece, v sub m e to the j theta, as a phasor. We're now going to say, oh, this is now the real part of some, and now you'll have to keep me honest and say, oh, is that the phasor or is that the magnitude? I'll try to just indicate with an overbar that this v sub m overbar is really a shorthand way of writing v sub m e to the j theta, where this is now our complex phasor. So if we are thinking of a voltage, we call it v sub m. That's now a voltage phasor. That's a complex number. What we have to remember is that if we wanted to go back into the time domain, we really need to have this sinusoidal piece associated with it. But to do the analysis, it's like taking a snapshot and saying, oh, what's everything look like now? Then everything's angles are going to be at some value, and that's why we keep track of their phase. And their magnitudes are going to be at some level. If we need to know what they look like in the time domain, then we can put in this omega t piece. That's why it's on the side. Here's our v of t. And inside the real brackets is this rotating phasor, and it's rotating counterclockwise with a frequency that we keep on the side of omega, radians per second. V sub m bar is the magnitude at an angle of theta, and that's the phasor representation of v of t. And note that that phasor is not a function of time. We're taking a snapshot, essentially, and saying, how does everything relate, magnitude and angle, at one instant of time? If I need to show you what's happening for all time, you just put in the appropriate cosine omega t. Now we convert this time domain waveform, v of t, little v of t, into a phasor by keeping the rotating phasor on the side, the e to the j omega t. And we can now say, oh, we have a voltage, it has a magnitude of v sub m, and it has a phase of theta. And we're now going to simply say, oh, we have this phasor, v sub m, which has a magnitude v sub m at an angle of theta. And that is not a function of time, and that allows us to avoid worrying about, explicitly, differentiation and integration. Differentiation now will be replaced by multiplication by j omega. Integration will be replaced by division by j omega. Easier to multiply and divide, maybe, than integrating and differentiating. That's the idea. There's our Phasor transform. And here's, I hope you get something out of this. I spent a lot of time trying to do this. So here's the spinning phasors and their time domain waveform. The phasor now I have sitting in, and this is the signal that I am, here's the v of t. There's the signal that we have, the real signal, cosine, of 2 pi 1t, what's the frequency? You can give me two equivalent answers. They just vary in their units. In hertz, what's the frequency of that cosine? How many cycles do you see each second of that cosine? 1. If you reported that frequency in radians per second, it would be 2 pi f. F is 1. It's now 2 pi. It has a phase shift of, in this case, 30 degrees, pi over 6. So at t equal to 0, if we needed to draw the phasor of that cosine time domain waveform, we would just have this length of one vector at 30 degrees. That's at t equals 0. And now I'm just sequencing through time. I'm marching time in the argument of that cosine, and at time equal to 2 over 24, or approximately 0.08 seconds, the argument has now changed to 60 degrees, pi over 3. The magnitude is not changing. We're just having a magnitude of 1 for this cosine. At a later time, t equal to 7 over 24, and these I've just picked somewhat conveniently, but you can hopefully see that time is increasing. The argument of that cosine is changing. It's now over to 135 degrees, or 3 pi over 4. Well, if we project those tips of the phasor onto the time waveform, you see that we extract or find the value of the time domain cosine waveform at that instant of time. At t equals 0, we now are not quite at 1. We are actually at some other value, which is, because where's the peak? The peak occurred before time t equals 0. This phasor is spinning around at a frequency of omega, which is 2 pi, or 1 hertz. So we're going 1 cycle per second in this case. So in 1 second, where will I be? Back to where I was in the phasor at time 0. But here, before that, I would actually have peaked. I would have been right there. I don't know why I did that. But before time t equals 0, I would be when the magnitude of that phasor projected onto the real line is giving me a value of 1. I project that phasor, I take the real component, that now projects, and that gives me a value right there. And that is consistent with what the time domain waveform cosine of 2 pi t plus 30 degrees is at time 0. It's let me find my crib sheet, 0.866. That's the value. Now we increase time a little bit. Here, this is time. On the waveform. We increase it a little bit to 0.08 seconds. And our phasor now has rotated. We project that tip of the phasor onto the real axis, and it gives us a value of 0.5. And that's consistent with what this sinusoidal signal is doing. We increase the time a little bit more. And now we're over at 135 degrees for the argument, the total, inside the cosine. Now we're down to minus 0.707. I know you're having fun spinning, so let's spin some more. They even have spinning classes, don't they? Do they still have those? We're doing that now with phasors. We're doing that in our head. Our heads are spinning. Hopefully this is making some sense. We spin a little bit more. We spin to 180 degrees, or pi. And we're now down to, what? 0.42 in time. We're now down to -1 at that cosine. Because at that value of time t, 10 over 24, the argument inside the cosine is actually pi. We go a little bit more. We spin a little bit further with time. We're now at 16 over 24, and we project that phasor onto the real line. It has no real component. It's 0. Finally, we go, oh, let's get back to when our angle is in fact 0, when phi is 2 pi. We're not quite all the way back to t equal to 1 yet, because we had an initial phase of 30 degrees. So when we get to 1 second, we'll be back at 30 degrees with that spinning phasor. All of that so that we can now try to convert back and forth from time domain to frequency domain, or phasor form, so that we don't have to keep track of all of these sines and cosines. If we now apply the Phasor transform to this time domain expression, how do we rewrite that? So now I want to say, oh, what is the phasor form of I? I'm going to call that now I bar. What's the first component of that? What's the if I now convert the first cosine component of that I of t into its phasor form, what would I write down? Magnitude, an angle. What flags didn't go up immediately? I'm not worrying about signs, am I? If I had a sine sitting in there, I would have to make sure and convert that to a cosine before I immediately put it into magnitude angle form. I can just put the next one into its magnitude angle. They're both at the same frequency, which I haven't even indicated, but I now have those two vectors that I'm trying to add. I can't just say that's 15. Do you see why? What's the answer in the back of the book? Now is when you would pull out your Black Friday purchase of a ruler and protractor and sketch this. You would say, oh, I'm 5 at 36 degrees, and I'm at 10 at minus 53. So this is supposed to be twice as long. This is now 36.87, and this is now minus 53.13, and that's a value of 10. You can now draw your parallelogram if you wanted to and obtain their sum vectorially or graphically. Or you could do all the projections. You could project this piece down, you could project that piece down, add those two components, and you see how far over on the real line you are. You could take this vertical piece and take away that vertical piece, and you can see, I hope, that if you put all of these together, you end up with a vector. This is the answer in the back of the book, which may not be very accurate, somewhere over there. If we now do the conversion, we now could say, oh, this is 5. The real part is cosine of 36.87 plus j sine of 36.87 plus 10 cosine of minus 53.13 plus j sine with a 10 in there, j10 sine of minus 53.13. You do all of that trigonometry and you end up with 10 minus j5. You can convert that to its polar form, which ends up being square root of 10 squared plus 5 squared at an angle of minus 5 over 10. Or this is 11.18 at an angle of minus 26.57 degrees. That's now how we have combined. This is now our I phasor, and I will let you go. You're spinning. Make sure you put your feet carefully down in front of you after all this spinning. I don't want anybody to fall. But we'll pick up here with going further in converting time domain differential equations into complex number-based algebraic solutions.